All right, let's take a look at this related rate problem, number 14. Got a right triangle, two aircraft approaching a field like so, coming toward the same point. And in this case, unlike the latter, everything has a rate of change. So that as the distances are decreasing, the distance between the two planes will obviously be decreasing. So that's what I was trying to indicate here between this blue dashed line, that purple dashed line, is that that distance is decreasing. So we won't wipe out dz dt like we did for the latter problem. So there's our standard related rate equation for triangle. Now, you can leave the 2's or divide by 2's, but sometimes I may leave them. It doesn't make any difference mathematically. But you can divide those 2's out and cancel all of them if you want to. So let's see. First aircraft is moving south at 260 meters per hour, kilometers per hour, and the west coming to 600 kilometers per hour. At what rate is the distance between them changing when the first aircraft is 60 kilometers from the field and the second is 25 kilometers from the field? Now, I guess you could make a case for this answer being negative, but I would be very careful on trying to set up a problem that would trick you into that. Yeah, I think that maybe my answer should be negative here. But like I said, I would not want that to happen to you. If you get this number right, I would want you to get the right answer. Because since those lengths of distances are decreasing, you could easily argue that this is negative 600 and negative 250, which would then make that answer negative. That would be the only difference. All the other numbers are in the correct location. Actually, I could have changed the word changing to decreasing, and then, like I explained earlier, positive answer for decrease. Saying decreasing, you can then say positive because the decrease would put the negative in front of it. So what do we have? Had to do Pythagorean theorem to get your z at that point. So when it's 60 kilometers away from the field, and the second one's 25 kilometers, I needed right triangle there to get that z. In other words, that's our z right there. So you solve that and get 65. And now we plug everything in. We're solving for dz dt, the distance between them changing, which would be right there. At what rate is it changing? So we've got 25 times 600 plus 60 y, and then 250 is what that rate's coming down from here. See, I have them labeled right there. There's the 600, 250. And then 65 times dz dt. So once you get that set up, pretty easy to solve. So it's roughly 461.54 kilometers per hour would be the rate of change at that location. Volume of a sphere increasing at 3 centimeters per cube per second. Find the rate of change of its surface area when the volume is 32 pi centimeters cubed. Yeah, so this one's a little tricky because you have to use two separate formulas. Now, ultimately, we're trying to find the rate of change of the surface area. Once again, these formulas would be provided, 4 pi r squared. So actually, I'll start with this part, but we have to go over to the other side to get some information. So the related rate equation would be dA dt equals 8 pi r dr dt. And the problem is we don't know what dr dt is. So that's where, so we have what r is. Actually, we don't have to, we have to solve for that too, excuse me. We don't know anything yet other than that equation. So what we have to do is come over to the one for the volume right here. Take it, the first thing I did was solve for r. So if you know that the volume itself is 32 pi over 3, there's your v. And you know 4/3 pi, that cancels, and it worked out pretty nicely here. 32 equals 4r cubed, r equals 2, so that's going to be my radius that goes right there. Now we need to get dr dt, so I have to get the related rate equation from the volume, because we do have a dv dt here. dv dt is 3 cubic centimeters per second, so then we can get dr dt from that. So we saw sphere earlier, so the first block of problems, 4 pi r squared is the related rate equation dr dt, dv dt. We have 3. We now know r is 2, so we could solve for dr dt, which is 3 divided by 16 pi. So we bring that number back up in over here, and then there we go. So pi's happen to cancel out conveniently, and all turns into a beautiful 3 there. So the units would be centimeters squared per second. So let's see. So there we go. So that was a little tricky. You had to work with both of these and get some information from the volume equation to plug it over into the area equation. A little bit of work, but makes you think a little bit. That's always good. All right, looks like we're now moving past the chapter 2 stuff, and now we're moving into chapter 3. We can find about all the graphing and stuff that the first and second derivative tell us. Critical numbers. Critical numbers come from 2 places. The most obvious is whatever makes the derivative equal to 0. What's less obvious and gives people fits on tests, and we will see this come up here shortly, but it's where you take the, if the derivative of a number is undefined, but yet the original function is not undefined, that's also a critical number. So to be a critical number, it has to be defined in the original function, first of all. So you might think, well, because you have to understand that the word critical is a specially defined term there. You might look at this and go, -3 makes the denominator 0, and that would be a discontinuity, and you would be correct. But discontinuities aren't, by definition, called critical numbers. I mean, they're just discontinuities. They certainly affect your graph and all that kind of stuff, but they are not critical numbers. So this one, you do the quotient rule, pretty straightforward there. I won't walk through that one. And you have this equation. Well, 4 over x plus 3 squared is never going to equal 0. And it's impossible. We're not talking about, the limit as it goes to infinity or something like that, but it's never going to exactly equal 0. So this function has no critical numbers. Now here we go. This is what you're looking for when you have that other definition of critical numbers that I was just saying, is when you have a fractional exponent and that fraction is less than 1. Because when you subtract 1, it will become negative. It's okay. So I'll point that out real quick. So here's my function. Let's take the derivative. It's going to be a chain rule. 3/5 comes down. You leave that alone. You subtract 1 from the exponent, makes negative 2/5. And you get a negative 2x from that derivative inside. So I kind of combined it and got a negative 6x over 5 times blah, blah, blah. So we set that equal to 0. Remember, anytime you're setting a fraction equal to 0, you're only setting the numerator equal to 0. So we don't care about that bottom part, at least not for this. You set the numerator equal to 0, so x equals 0. So for sure we have a critical value by that definition. Those are the ones that give you the horizontal tangents like we have here. However, this original function has no discontinuities. Because of that denominator, and anytime you have a fractional exponent where the denominator is odd, you don't have discontinuities because you can take the odd root of positive or negative numbers. So no discontinuities. However, notice that because when this derivative produces a negative exponent, that's all where that other definition is coming from. You drop that to the bottom. Notice that you can take 9 minus x squared plus and minus 3 would make that 0 in the denominator, which makes the derivative undefined. Well, like I just said, there are no discontinuities, so that's that second part of that definition of critical numbers. If it's undefined in the derivative, but it's still defined in the original function, those are critical numbers. And that's always a very difficult point you get across, even to students when I'm explaining this to face, or even if they get it, it doesn't necessarily always translate to when they're actually trying to do some problems involving it. They might understand it when I say it, but so this negative 3 and positive 3 are undefined in the derivative, but they aren't in the original function. So that makes them be critical numbers. So you have 3 critical numbers, net plus and minus 3 and 0. Now you might look back up here for a second and go, hey, negative 3 is undefined in the derivative. Yes, it is. But it's also undefined in the original function. Therefore, it's not a critical number. A critical number has to be a number that exists on the graph. It can't be a discontinuity. So there goes that theory. Sometimes I might get that question asked, when I'm teaching a face-to-face class. So if it's undefined in the original function, it has no chance of being a critical number. All right, this one's a nice and easy one. I like this one. Take the derivative. I shouldn't have to explain that by now, I think. Factor out of 12x squared. I didn't even finish this one. It was so easy, but I'll be happy to explain it. So you set 12x squared equal to 0. That would start to make x equal 0. And then x minus 1 equals 0 would be 1. So you would get 0 and 1 as your 2 critical numbers. Well, that one was nice and easy. And once again, it's kind of like maybe my order of these is a little bit weird. The first 2 were more challenging than this one, but that's okay. I do have this organized where I think most of the problems are all in the same general area, as you start from the beginning and go to the end in relation to the section numbers. But maybe not, within each section, they're in the same order. Oh, trig functions. Absolute mins and max. All right, very important to remember this is as long as your function is continuous on a closed interval, no discontinuities, you're absolutely guaranteed to get an absolute min and a max. Now, they could equal each other. The only way that could happen, though, is if you had a horizontal line. But anyway, as long as it's continuous, an answer choice of no absolute min or no absolute max is impossible. You don't pick that ever as an answer if it's a multiple choice test or like on a quiz or something like that. So this function is cosine of x minus x. No problem. Cosine, you can put any number in there you want, you'll get an answer. X, of course, no problem, no discontinuity. So that absolutely, positively guarantees by the theorem, perhaps I can't remember the number of the theorem in the book, but as long as you're continuous and closed, you have a min and a max for sure. So don't fall into some trap that says no max, no min. No. Take the derivative. Derivative cosine will be negative sine. Derivative negative x will be negative 1. Set that equal to 0. And, I always provide the unit circle. So you could find, because anyway, what you're looking for here is the answer is going to come from the following. It's going to come from either the endpoints or any critical numbers that fall inside the interval. Let me repeat that. Inside the interval. So I don't worry about putting this low to high. What I always do is put the two endpoints in there first, because I know they're going to be tested. That's by definition, you're testing the endpoints. Now you may not have any critical numbers that fit in there, but what you have to be real careful though is if you solve and you get a critical number that's not in your interval, do not use it in this chart right here. Let's say that your interval went from 0 to 4, and you got critical numbers of plus and minus 2 by solving it algebraically. It probably means you did it correct. Like so, let's say you got x squared equals, it reduced down to x squared equals 4. That would definitely be plus and minus 2, but you would not use negative 2 because it's not in the interval. So we can only use things that are in the interval. So always watch for that. With that being said, sine of x is negative 1. 3 pi over 2 would be that critical number. 3 pi over 2 is a critical number, and it's between 0 and 2 pi, so we can use it. So I didn't show the work on these, but you could do these in a calculator, you know, with a t-chart. In fact, I think I can do that real quick here. So it was cos x minus x. Quit out of that. I'll make sure I'm in radian mode here. Yeah, radian mode. The interval's in radian mode. So, all right, see it? Radian mode. So I have the y in there. Do not plug your values back into the derivative. They go into the original function. And let's see, I want to get rid of that though. I want my table set to be independent values. You want the dependent to be auto, but your independent x, you want to be asked when you're just going to manually type in some values. So of course this is not going to show the pi symbol here, but you can see me entering it here. 3. Where are you? Pi. There you are. Pi divided by 2. It'll convert that to decimal radians. And 2 pi. And there we go. So let me come back. I think I'll screenshot that. Come down here. Oh, looks like I did. There's a screenshot for another one. Move it up. So it looks like it chose to do it that one, just didn't do it for this one, but that's all right. Put it in there, save it. Post it this way in the future now. All right, so there you see from my hand-drawn one there. So the 1 minus 2 pi, that's going to be your oh, they're out of order. Excuse me. I didn't. I guess I could change that. Yeah, I might as well change it. Technically, I don't have to, but that would be kind of confusing, wouldn't it? Somebody 2 pi, then 3 pi divided by 2. Now let's. Yeah, that probably would have bugged me if I realized I hadn't changed that. From a mathematical standpoint, it's no problem, but it would not line up with what our hand wrote there, so that could be I don't want to cause any confusions. So yeah, 1 minus 2 pi would be about negative 5.28. And then negative 3 pi over 2 is the negative 4.172. So your minimum is going to be, I didn't wrote it out officially here, but decimal's probably okay. But so the max, the min, excuse me, negative 5.2 is smaller than negative 4.7, so it is that middle one, 2 pi, and then the max, of course, 1 is the largest of those three y's. So it would occur at 0, 1, and then the min is 2 pi, comma, 1 minus 2 pi. One thing to keep in mind when you're doing this stuff all through chapter 3, not just here or whatever, but often I'll have people that they plug their critical numbers. I'm not sure where they're plugging stuff back in, and anytime you're trying to find the y value, you want to plug into the original function. A lot of times people will go, I keep plugging these back in, I keep getting 0 for all the answers. And that's because what they're doing is taking critical numbers and they're plugging them back into the derivative. So if you set something equal to 0 to find that value, it would only make sense that if you plugged it back into that, you would get 0. Then they realize their mistake and everybody has a good laugh. Okay, another trig function. I don't like these to get too complicated. So we have sine plus cos on the same thing on the closed interval 0 to 2 pi. That function's continuous. There's no doubt we have answers. We would not pick, under any circumstance, no absolute min or no absolute max. So derivative of sine is cosine. Derivative of cosine is negative sine. So you set that equal to 0. So basically you're looking for anywhere where sine x equals cos x. And you can conveniently find that on the unit circle at pi over 4 and 5 pi over 4. Because at pi over 4, they are both square root of 2 over 2. And at 5 pi over 4, they are both negative square root of 2 over 2. So you see, I did the same thing. I put my 0 and 2 pi in there first because I knew no matter what, they were going to be there because they're the endpoints. Then I waited to see if anything comes in with it. Well, both pi over 4 and 5 pi over 4 fit in that interval. They're both in there, so we want them both. So there's two critical numbers, the two endpoints, and I plug them back into the original function because, like I said, if you'd have plugged that pi over 4 and 5 pi over 4 back into the derivative, you would have gotten zeros there because that's where would have got that 0 right there. So plug them into the original. See, I did it down here, and then I also did it with exact answers. So you've got pi over 2 when you put pi over 4 in there. Yeah, basically because you have pi over 2, square root of 2, excuse me. You have the square root of 2 over 2 plus the square root of 2 over 2. Half of something plus half of something is 1 of something. So you have the square root of 2 and negative down here. So out of all those, I'm going to say that negative pi over 2 is my smallest one for sure. There's my min, so it's at the point 5 pi over 4, negative root 2. And then out of all those positive y values, square root of 2 is the largest, so you can see it down here actually better. Positive 1.41 pi over 4 root 2. And there's your max and min. Another absolute extrema, same process. So notice I have negative 1, comma 2, so I got both those in there. Now, I quite often, and this might have come up even on the exam 1, if I remember correctly, but when I have something with just a number on top and a variable on bottom, instead of doing the quotient rule, I usually just bring that up and do a general power / chain rule. But if you do a quotient rule correctly, it's going to be fine, but I just find this to be a little more efficient, but that's okay if you want to do a quotient rule. So what do we got here? We've got, so you see I brought that up, and okay, I left out a step here. That would have been 10x squared plus 1 to the negative 1. Let's put y equals. pretty ugly looking, then took the derivative. I wrote f prime of x. But for those of you that, if you're taking face-to-face classes with me there, versus whether it's online, I'm real picky about this. Wouldn't matter so much if you're taking a test from the multiple choice test for online, but I always have to have proper notation that when you take a derivative, that's why I put that y there, you have to put prime. Now, it's okay what I did here. I'm not picky about that. If the original function said y equals, and you don't put y prime, you put f prime of x like I did, that's all right too. But I'm always, real big about saying don't just write the derivative without putting something in front of it, notation-wise. That's just bad form, basically. Because the derivative is a function, it's not an expression, so it does need something defining it, just like y equals does. Bring down the negative 1 makes negative 10, subtract 1 makes negative 2. Derivative of the inside is 2x. So took the negative 10 times 2x is negative 20x. Drop that back down to the bottom, made it x plus 1 squared, which is what you would have gotten via quotient rule. And we have, remember once again, like I said, anytime you set a fraction equal to 0, it'll probably sound like a broken record, but it doesn't hurt to hear that. Of course, none of you know what a record is, but set that equal to 0. You only have to set the numerator equal to 0. Well, some of you might know what a record is. I think vinyl is starting to make a little bit of a comeback for audiophile musicians, music fans. So negative 20x equals 0. And that just means x would equal 0. So and 0 is in our interval. It fits. So we want to count it. All right, so I'm not going to worry about putting the calculator t-chart in there. So if you plug negative 1 into the original function, you'll get 5. Plug in 2, you'll get 2. Plug in 0, you'll get 10 over 1, which is 10. So the min will be 2. It's the smallest of the three y's. So at 2, 2 is your min. 0, 10 is your max. And there you have it. So once you get the derivative correct here, to get that other critical number, that problem shouldn't be too bad. Determine from a graph whether it has absolute extreme values on either A or B. Definitely has a maximum. No letter there, but you might be wondering, why is that not a min right over there where that A is? It's not, because there's a hole there. Had there been a dot there, there would have been a min. Because remember, a hole, you're never quite touching it. So let's say that hole was at a value on y, on the y-axis right here. Let's say that was a 1, just for grins. Well, see, it's never hitting that, because then you could argue that, you could argue back and forth with somebody. Well, I think the min is 1.1. The next person could go 1.01. The next person could go 1.001, and it would never end. So you never are reaching a specific minimum because of those holes there. So, but if that would have been a dot, yes, it would have been a min. That's why it's only an absolute max. Absolute extreme again. Once again, this would have made more sense as an easier one going first, but that's all right. Might be doing the more challenging ones first. That's better. I don't know. Okay, I want to go pretty quickly here. This one's really easy. 0 and 3 go in there. This is simple derivative, 2x minus 2. That would be your critical number of x is 1. 1 does fit in your interval, so it does go in there. I'm hoping I have one where we throw one out, because that's very important. So put the values into the y, not the derivative. Plug them in there. So you plug 0, 3, and 1, and you'll get 1, 4, 0. The minimum would be right here. The smallest of those y's is 0, so it's 1, 0. The largest of the y's is 4, so you have a max of 3, 4. No, I'm okay. I'm surprised that none of these, I guess we'd ever tossed any of these out, but be very attentive to that. I'm hoping I had a quiz problem that did, but I certainly have it in my notes. I really can't fix this solution thing right now. I can at least go to the notes just for a second here and show you. Yeah, well, there was this example, kind of carries on the next page, but see, here was one where you had 0 to 3, and you did the derivative. It's not very difficult. This one isn't, but shows you x squared. But remember, always be careful when you have x squared equals positive number. You've got two answers, but you would not include -1 on your chart here because -1 does not fit between 0 and 3. So please pay attention to that. Probably need to update this review. Let's just change out one of these problems would actually be good enough. Here's a Rolle's theorem problem. Rolle's theorem basically says that if function's got to be continuous from a to b, and that certainly is true for sine of x, and then the two y values have to equal each other at each endpoint. If that's true, you're guaranteed at least one value where the derivative will equal 0, basically one horizontal tangent. So you could have one, you could have more. Like suppose you had something look like this. These, pretend like, I'm not sure they're perfectly horizontal, but just for this exercise, pretend like they're equal. And so let's say your function was continuous and maybe did something like this. So for the Rolle's theorem, they have to be equal. The y values have to be equal, and you're guaranteed to at least get one value c. Here you would have gotten two values c. Well, that's a pretty terrible freehand. Or that's a horizontal tangent line, as bad as that looks. Here's another one. It would have been those two locations. So you see what I did over here was I plugged in the pi over 6 and the 5 pi over 6, and they both produce 1/2. So that means this theorem is valid and it is continuous. So that means you just set the derivative equal to that value, provided it's in the interval pi over 6 to 5 pi over 6. Anyway, and that, okay, I'll mention something here. So you take the unit circle. Pi over 6 is in quadrant 1, 5 pi over 6 is in quadrant 2. This is a good example, even though I don't have it written here, about something you have to actually ignore here, and I don't mention that. But anyway, you set this derivative to a sine of cosine 0. And I have pi over 2, but cosine also equals 0 at 3 pi over 2, but 3 pi over 2 is not in the interval. So maybe I can actually write this in here. Although, let's see. It's not an interval. I'll just put not. Oh, it's getting ugly here. It's not included. Or not, I'll just say not in the interval. Three pi over 2 is not in the interval. So don't use it So only pi over 2 fits. So in that particular interval, from pi over 6 to 5 pi over 6, it's only going to have one horizontal tangent there at pi over 2. Okay, Rolle's theorem. What do we have here? All right, this one's, well, okay, it's telling you it does not apply. So there's two ways it cannot apply. Answer B is a possibility. I didn't bother to circle the answer here, so, but in this case, if you put -2 and you put 0 in there, you're going to get the same y value. You'll have -1 squared, which is 1, or you have 1 squared. That's not, that could have been a reason, but it's not a reason. It's the fact that you have a discontinuity, or also not different. Yeah, not continuous. So basically, not continuous, not differentiable. Yeah, it's got to be continuous and differentiable, meaning no. You know, we learn continuous and differentiable aren't necessarily the same thing, because you can be continuous and not be differentiable, like at a sharp point or something like that. So I didn't circle this, but should have had this. Look a little better here. All right, should be D. But also should have said not differentiable there. I probably should check the original form. Make sure that that verifies what this says. Okay, so yeah, right here, 25 was D. It's a discontinuity. Rolle's theorem does not apply, and it's not differentiable at x equals 1, -1. So actually, both of those are right. I don't think I can fix that too well right now, so. Mean value theorem. Mean value theorem. F of A does not have to equal F of B. It just has to be continuous and differentiable in the interval. But in other words, the endpoints don't have to equal each other. So unlike the Rolle's theorems, you don't have to actually check that. But what you do then is, if it looks like this function, 3x minus x squared, any straightforward polynomial is going to be continuous and differentiable. So you're set there, so that's no problem. So what we have to do is we have to find the values of c. So in setting the derivative equal to 0, we are setting the derivative equal to the slope between those 2 points, the secant line slope. And if you look at my notes, you can see, so they don't have to be the same thing. They can be, let's say point here, and then maybe your graph does this, and you're trying to find where it equals that slope, parallel to that slope. So that'll be like here, oops, and here, oops, yeah, like that. So it's parallel to that slope. Now, if that slope happened to be 0, then it just turned out that the mean value theorem is, so like it's basically the Rolle's theorem is a subset of the mean value theorem, where it just happened to be at the slope of 0. Okay. Doesn't matter what you do first. I went in and found that slope. So f of 3. Put 3 in here. You get 3 times 3 minus 3 squared. That'll be 0. Of course, 3 minus 2 on the bottom is 1. So that goes away. F of 2. 3 times 2 is 6. Minus 4 is 2. There's your 2. 0 minus 2 is negative 2. So we want to find the value c where you set the derivative of the function equal to negative 2. So easy derivative is just 3 minus 2x. On my face-to-face class, if this was done handwritten, I always like to do it with letter C, but I don't penalize someone if they just use letter X here instead of C. I only penalize if they don't put the derivative notation. Yeah, so if you just said 3 minus 2x equals negative 2, that's okay. But this is right. The derivative of 3 minus 2c equals negative 2. Simple algebra. You get 5 halves, and 5 halves is between 2 and 3. So what this theorem says is, yeah, I guess it could be possible you might get one that doesn't fit in there, but you're absolutely guaranteed to get at least one number that does, no doubt. Minimum one, maybe more. So there's no way you could work this problem out and then come to the conclusion that there are no values that satisfy it. That's impossible. Because if it meets the conditions, it will guarantee to satisfy it with at least one number, possibly more. I'm certainly not interested in making this that complex for exam purposes, or I want it to be too difficult, but so just keep that in mind.